Hello, today we are here to talk about cooperation, and from an evolutionary biology perspective, a discussion of cooperation is first and foremost a discussion of altruism. So I'll define what these two words mean and what we talk about when we talk about cooperation, because humans are quite unique. In 2005, Joan Silk came out with a study of chimpanzee helping behavior. So you had two chimpanzees in pens next to one another. One chimpanzee could pull a rope and deliver treats to the chimpanzee in the pen next door. And what she found was that chimpanzees were incredibly indifferent to the rewards that they were giving to their neighbors. And this is generally the case. Chimpanzees are not nearly cooperative as humans are. We do see them engaging in cooperative behaviors, like this picture on the right. This is a territory patrol. They're going out together and patrolling their territory, and it requires several individuals to work together. And we do know that chimpanzees are capable of feeling empathy, but again, it's not nearly to the same levels that humans can do these behaviors. So why is this the case? Well, Sarah Hrdy, as you have been reading in Mothers and Others, thinks this is mostly due to what we call cooperative breeding. And this is the problem with cooperative, this is not maybe the problem, but this is what's at stake when you're a cooperative breeder. You can see this big chart, looks like a dome on the left, and this is the number of kids that a Ache woman has. The Ache are a tribe in the Amazon living very similarly at the time the data was collected to the Yanomamo. So around the age of 20, she has her first kid. She'll have her second kid on average around the age of 25. By about 30, she has her third kid, and around the age of 35, she has 4 dependents. That's a lot of dependents at the age of 35, and it'd be very difficult for this woman as an independent forager alone in the forest to care for all of these 4 dependents. And we can compare this to data, the smaller graph on the right. This is data from the Kung, who are a tribe living in the Kalahari Desert, also foragers, but in quite a different environment, and we see a very similar pattern. By about the age of 35, she has 4 dependent offspring. So we can look at what the calorie deficits are. Let's just talk about calories. I'm not talking about, changing the diapers or anything like this. Just talk about caloric needs. So in the Ache, this is a graph of female production in terms of calories versus consumption. How many calories is she bringing into the household versus what is she eating? And let's just look at the solid dark line. This is her production. Calories she's bringing into the household. You can see between the ages of 0 and 5, the solid dark line is quite close to 0, so she's not bringing in anything at all. By around the age of 25, women in this society are bringing in about 2,000 calories a day. And by around the age of 50, that's up to almost 3,000, and then it drops off again between the ages of 70 and 75. So she's doing pretty good. However, women at these ages are consuming, between the ages of 0 and about 40, are consuming a lot more calories than they're producing. And you can see that in the dashed line. About the age of 5, she's consuming, almost 2,000 calories a day. Between 20 and let's say 55 she's consuming about 2,500 calories a day. So for only a small amount of time in her life, about 25 years, are Ache women actually producing more calories than they're consuming? For most of their lives, they are consuming a much larger number of calories than they are consuming, and these have to come from somebody else. There has to be some helping behavior going on here. This is just her own calorie consumption. This isn't including the calorie consumption of all of those dependent offspring. If we compare this to the chimpanzee data, the triangles and pluses that you see here, for the most part, chimpanzees are producing as many calories as they're consuming. There's a small period of infancy when chimpanzees are dependent on their mothers and they're getting most of their calories from their mothers, but overall, chimpanzees don't have this production-consumption gap that humans do. We can look at the male data just for comparison. Looks a bit different because of hunting patterns versus mostly female foraging. And there is this huge excess of calories that males are producing during middle age. Probably a lot of this is going to women and their dependent offspring. but they still have dependent periods in their lives also. And again, comparing to chimpanzees, we see what a different pattern humans have. And the fact that there's calorie overproduction by individuals of certain ages and calorie underproduction by individuals at other times in their life, we know that there has to be some sort of exchange of calories. Hunters and foragers who are bringing back extra calories are sharing that with other individuals, and that is one of the keys that allows us to have all of these stacked dependent offspring, the fact that there are other people bringing food into the household. And this is what Sarah Hardy means by humans are cooperative breeders. Humans are often dependent on others. Individuals who cooperate have higher survival and reproductive success. So because we've had this history of cooperating with one another, those cooperators were more successful, had more kids, more likely to survive, and left those behavioral dispositions to us today so we can see patterns like we do in the Aceh. The big question, though, is why are we so much more cooperative than other apes? What are they missing out on? They do have empathetic abilities. They do engage in small-scale cooperation. Why do we take this to the extreme? So as I said, this is also going to be a discussion of altruism, and this is where we're going to start thinking through some of these questions. So altruism is defined as an act that confers a benefit on a recipient at some cost to the donor. So you would do something to help someone else, you would pay a cost, you pay calories to lift something for them or give them some money for gas, and you get nothing back, absolutely nothing back. This is altruistic behavior. We see a lot of what we think is altruism in the animal and human world. So meerkats will spend time not foraging, not grooming, not trying to find mates. They'll spend a lot of time just detecting predators. So they're paying a cost, they're giving up a lot of other opportunities to provide a benefit to other individuals. They'll give an alarm and all of the other meerkats who are out foraging or mating will dive down into the holes. We know that altruism includes allomothering, so taking care of other individuals' children. This could be lactating, this could be grooming, this could just be babysitting. Blood donation is a good example in humans. If you've ever given blood to the Red Cross, you've paid a cost in blood to provide a benefit to someone else. Maybe you get a cookie to help bring up your blood sugar afterwards, but there's not really so much of a benefit to you. Food sharing in chimpanzees is another example. Someone's giving up calories to provide them to someone else. In this case, you can see a mother begging for calories from the males who had a successful hunt. You can see her baby there on her stomach. But altruism is actually a mystery when we think about this from an evolutionary perspective. Why would other people sacrifice their lives or pay costs for the good of others? And these kamikaze pilots from World War II are a really good example. These are reproductively aged men. They have signed up to go and fly planes at enemy ships. They are giving up all of their survival, and very few of them have reproduced before they sign up to become kamikaze pilots. They won't leave any of their genes to future generations. Everybody with a helping instinct is dying before they reproduce. Well, not everybody, but in this case, all of these pilots have a helping instinct, and they're dying before they reproduce. This doesn't make any evolutionary sense. Why should we see this behavior if everybody who does it dies without leaving kids? So here's the reasoning. If natural selection promotes behavior that causes individuals to act for their own best interests, how could behavior evolve, which entails increasing the reproductive success of others at the expense of one's own self? How could we see helping a behavior evolve if everybody who helps produces either no or very few offspring, or at least a lot less than selfish individuals who just take the benefit and use it for their own good? So it's really an evolutionary mystery of why we should ever see altruistic behavior. And the answer is that most altruism is really called cooperation. And individuals who are helping often get paid back in unseen ways. Now, humans are unique, and we'll discuss this at the end, because this example of kamikaze pilots is definitely altruism. It's not cooperation. But in most animal examples, individuals are getting paid back in ways that are not immediately apparent. And one of the ways they can get paid back is by cooperating with kin. And to understand this, we have to understand a concept called inclusive fitness. So when you think about an individual's survival and reproductive success, we can call it by another name. We can call it fitness. Again, remember, fitness is not strength or speed or size in the natural world. We think of fitness as fit to the environment. And the measure of fitness is your contribution to future generations. So you're fit to your environment, you've inherited characteristics that make you successful. This success is measured in fitness because success is measured by your contribution to future generations. The more successful you are at surviving and reproducing, the more of your genes get passed along. So we can actually measure fitness in two ways, one of which is direct fitness, your own survival and reproductive success. But of course, that's not the only way to get your genes out into future generations, because other people have your genes, and those people are your kin, your relatives. And their fitness is called your indirect fitness. So if you have a gene for helping and your sister has the same gene for helping, her success passing on that gene is also your success because your genes have got passed on through your relatives. So together, combining your own survival and reproductive success with the genes that you have shared with your kin, we combine these to call this inclusive fitness. It includes your direct fitness and your indirect fitness. And this is such a powerful concept that it gets its own name. It's called kin selection. It's a type of natural selection that selects for behaviors that increase the inclusive fitness of the donor. So kin selection promotes behaviors that maximize your inclusive fitness. So in some cases, if you have the chance to help kin reproduce a lot, if you help them out, they reproduce a lot, you're increasing your inclusive fitness because you're increasing your indirect fitness, because you're increasing the proportion of genes that you share with your relatives that are going to be present in future generations. Now, if you have questions about this, it's a complicated topic. Please email me, call me, come to office hours, put a question on the discussion board, and I'm really happy to talk you through this in more detail. So we'll work through some examples, don't worry. All right, so inclusive fitness, why help kin? Individuals have a vested interest in the genetic success of their relatives, their relations. This is a macaque family, a grandmother, mother, and granddaughters, and the grandmother helps the mother and the granddaughters because her genes, she's passed her genes on to the mother. The mother has passed the grandmother's genes on to her granddaughters, so by helping her relatives, her granddaughters, she's really helping the success of her own genes in the population. So this is one way that helping behavior can actually increase survival and reproductive success, can increase fitness, can increase the proportion of helpers in future generations, because by helping, individuals are essentially paying an investment and they're getting their money back on their investment, and so their own success increases. And there's a really simple rule of thumb to think about whether individuals should help kin or not, and that was developed by W.D. Hamilton. It's called Hamilton's Rule. It's on the next slide. Hamilton realized that individuals can increase contributions to future generations indirectly by helping their kin. And his rule is, you aid your relatives as long as you follow BR greater than C. B stands for the benefit that your relative is getting. R stands for the relatedness. How closely related is that person to you? And C is the cost. So the cost is the investment that you paid. The benefit that your relative is getting times how related they are to you is what you're getting back out of that investment. So if they're getting a large benefit, we have to multiply that by the percentage of genes that they share. You share half of your genes with your brother, for example. So if you pay a cost to help your brother, if the benefit your brother gets times 1/2, because that's on average how many genes you share, if that's larger than your cost, then you're recouping your losses. And this is a really cool concept because it's what we consider to be an evolved decision-making mechanism. So a lot of behavior is actually really flexible and responsive to the environment. A lot of behavior is you're confronted with a situation and you have to make a decision. And these decision-making mechanisms, these rules, these patterns for how you should respond to certain situations, these are the evolved behavior, not strict patterns that you have to follow without any consideration of the environment. It's the decision-making, the mechanism that's at stake here. And so I think this is a really cool concept. But let's step back and let's walk through Hamilton's rule because I want to show you what it really means. So Hamilton's rule tells us whether or not we should help a relative. Now I would recommend you stop and pay attention as I walk through what all this math means. So we know what some of the letters in these equations mean, and don't worry, this is just simple algebra, and most of these are going to go away, and we'll only have BR equals C, or sorry, greater than C. So the only thing we don't know here is W1 and W2. That's just your direct fitness and your indirect fitness. So W1 is your own survival and reproductive success. W2 is the survival and reproductive success of your relative. And again, we think about this as potential contributions to future generations. A very simple way to think about this is number of kids or number of grandkids. So let's walk through here. We're just comparing two things, either side of this equation. On one side, we have your fitness with helping behavior. Should you help your brother? Is that greater than not helping him? So we're just going to figure out which side's bigger. If the fitness side with the helping behavior is bigger than fitness without helping, then Hamilton says you should help your relative. Okay, so first step we do on the second line here, we're going to take everything out of parentheses, and that allows us to remove most of these letters. So we see here that on the left side, W1 cancels out with the W1 on the right side. Good, so those are going to go away. Also, W2R on the left side cancels out with W2R on the right side. And so all of this reduces down to Hamilton's rule. Is the benefit times the relatedness greater than the cost that you've paid? And we can see from this that, first of all, you're more likely to help those most closely related to you. So anyone who's removed from you by just one step, so your siblings, your parents, and your offspring, all of those individuals share half their genes with you. You know this. You get half your genes from mom, half your genes from dad, so you're related to them by half. You're related to your grandparents and your grandchildren by 1/4. So you have half of your parents' genes, and they have half of each of their parents' genes. So any one grandparent you're related to by 1/4. And on and on. So first cousins, 12.5%, and the further distantly related you are from someone, the smaller percentage of genes that you share. So because the benefit that the individual who was helped is getting, you only care about how much is coming back to you, the percentage that's coming back to your genes. So the smaller R is, the more distantly related someone is to you, the less likely you are to help them. The less likely that BR is going to be greater than C. So let's do a little practice run. I'm going to give you some numbers. Should you help this person, let's say you're deciding to help your brother, the benefit he's getting is 3 fitness points. The relatedness, he's related to you by half. The cost that you're paying to help him is 1 fitness point. So go ahead and plug it into the equation, pause the video and work it out, and when you come back, I'll give you the answer. Okay, so hopefully you've done the calculation. 3 times 0.5, is that greater than 1? And the answer is yes. BR in this case is greater than C. So you should help your brother in this case. Let's walk through a couple of real-world examples. Ground squirrels are one of my favorite examples. One of the things that they do is they scan for predators and give alarm calls. And this is really dangerous because you can imagine a hawk is flying over the meadow, and all of a sudden one ground squirrel sees it and stands up and starts yelling its head off. This squirrel that's giving the alarm call is most likely to be noticed by the hawk and is at a much greater risk of predation. So the ground squirrel is paying the cost of giving up its life to help out other ground squirrels who hear the call and head for their burrows. And those who do hear the call are much more likely to escape and live to be a ground squirrel another day. And researchers have spent a lot of time hanging out in meadows with ground squirrels, and they know who's related to who. And they found out that ground squirrels are much more likely to stand up and give these alarm calls when their kin are nearby. If they're around strangers, they're much less likely to pay the cost because they're not recouping that benefit. Florida scrub jays are another cool example. Most scrub jays will hang around after the first year, and they'll stay with their parents for another season. And what they're doing is helping raise the next set of brothers and sisters. So this is a benefit that their parents and their siblings are getting, but they're giving up their own chance to breed. They haven't gone out and found their own territory that season. Instead of going out and finding mates, they're hanging out and helping raise relatives. And this increases their indirect fitness and therefore their inclusive fitness, because their parents have more offspring and they have more siblings, and so the scrub jays that stay to help have increased contributions to future generations. Now, in this case, the scrub jays that are staying to help, they are giving up their own chance to breed, but perhaps their own chance to breed is pretty small. That first season, they don't have a territory, they're not finding a lot of food, they're not very big yet. So it does make sense they're giving up maybe some small direct fitness for a much larger indirect fitness, and they're getting paid back for their helping behavior. The main difference between humans and other species is that cooperation in most species involves relatively small numbers. We don't see warfare in other species with thousands of participants. We see small groups, usually a handful of individuals. And mostly for other species, cooperation involves close kin. And this is what we're going to be talking about later in the course, about how we get cooperation outside of kin. The social insects like ants, bees, wasps, and termites are very helpful for one another. They live in colonies and they help the queen reproduce, but they have a really unique inheritance system where the females are actually more closely related to their own sisters than to their own offspring. So instead of helping offspring, they tend to help their sisters. But among humans, we often help large numbers of people, oftentimes strangers. And so this data comes from some researchers who were working in New York City, and they just stopped people on the street and asked them, "Oh, excuse me, could you give me a dime?" The person who gives them a dime is paying a cost, 10 cents, to give a benefit to this stranger, and about 40% of people did. They said, "Excuse me, can you tell me what your name is? Can you give me change for a quarter? Can you tell me how to get to Times Square?" And in most cases, everybody was very, very helpful to strangers on the street. And this is why human cooperation is unique, because it's much more like altruism than any other species approach. So we help in a lot of ways. We pick up litter, we donate to charity, we tip, we give blood, we adopt individuals we're not related to. And cooperation can be anonymous, so nobody knows who's giving the benefit. You can't recoup your loss if no one knows who you are. It tends to favor non-kin, oftentimes without reciprocity, and oftentimes entirely voluntary. So we'll get into some of these problems later on in the course, but for now we're going to move on and discuss how do you know who your kin are in the next several presentations. Thank you for listening.